Hello friends, welcome you all to the 14th lecture on function analysis and its applications. In this lecture, we will discuss on norm of bounded linear transformations and some related theorems. This is the content of today's lecture. Norm of bounded linear transformation or continuous linear transformation. Definition. Let n and n dash be normed linear spaces over the field F and let T be a bounded linear transformation of n into n dash. Then the norm of T is defined by norm of T is equal to infimum k such that norm of Tx less or equal to k norm x, where x belonging to n, because we have the mapping T such that n to n dash. Okay, x is the element of n and Tx is the element of n dash. If satisfies this condition, then we can say that T is bounded linear transformation. Okay, so this is the notation norm T here defined. Here we have the condition norm of Tx less or equal to k norm x. The smallest possible value of k in equation 1 is called the norm of T. Okay, this inequality can be written as norm of Tx upon norm of x for x not equal to 0. We have the norm T. Okay, this shows that the infimum k must be as large as the supremum of the expression on the left side of equation 2 when x not equal to 0. That is, this one supremum of this and infimum of k. Hence, norm of T can be defined by the following formula. Norm T equal to supremum of norm Tx upon norm x for all x belonging to n and x not equal to 0. Theorem. Let n and n dash be normed linear spaces over the field F and the mapping T such that n to n dash a bounded linear transformation, then norm of T can be expressed by any one of the following formula. First, norm of T equal to supremum of norm Tx such that x belonging to n, norm x less or equal to 1. Second, norm T is equal to supremum of norm Tx such that x belonging to n and norm x is equal to 1. Third, norm T is equal to supremum of norm Tx upon norm x such that x belonging to n, x not equal to 0. And fourth, norm of T is equal to infimum k, k positive, where norm of Tx less or equal to k norm x for all x belonging to n. This condition, norm of Tx less or equal to k norm x, it can be written as norm of Tx less or equal to norm of T norm of x. Okay, why? Because primum value of all bounded linear transformation, that is a real number, so it can be denoted by the norm T, that is constant. Okay, so this is the norm T constant, so we can write norm of Tx less or equal to norm T norm x. We replace the k by norm T. Okay, so these all four conditions are equivalent. So let us prove these are equal. Assume that A gives the definition of norm T. If we denote the right hand side of the expression B, C, D respectively by M2, M3 and M4, then it is enough to prove that norm T is equal to M2 is equal to M3 is equal to M4. Just notation, we consider the first condition gives the definition of norm T and other three we can prove equal. Okay, let us prove this. Since x belonging to n, norm x is equal to 1 is a subset of x belonging to n such that norm x less or equal to 1. Okay, this is obvious because here norm x is equal to 1 and here so many value of norm x including 1 and less than 1. So we can write this. It follows that primum of norm Tx such that x belonging to n norm x is equal to 1 less or equal to supremum of norm Tx such that x belonging to n norm x less or equal to 1. Okay, as per this condition, supremum of norm Tx with this condition, this is less or equal to the supremum of norm Tx with this condition. Okay, because here the norm Tx has the value of x belonging to n, norm x is equal to 1 and here norm x less or equal to 1 and same supremum norm Tx defined. So it has more value, okay, because it has norm x less or equal to 1, here norm x is equal to 1. Thus here this condition already we consider the definition of norm T. Okay, so and this one denoted by M2. Then we can say that M2 less or equal to norm T. Equation 1. Again, since T is linear transformation, we can write M3. What is M3? This is condition C. It is denoted by M3. M3 is equal to supremum norm of Tx upon norm x for all x belonging to n and x not equal to 0. Okay, this. Suppose x upon norm x is y. Here norm x, already here x belonging to n, that is vector, okay, and we know that if x is vector and alpha x, where alpha is scalar, then alpha x also vector. So here norm x can be treated as constant. So x upon norm x can be treated as vector and we consider here x upon norm x is a vector y. Okay, taking the modulus both sides of this, so norm of y equal to norm of x upon norm x. Norm x already is scalar, so we can write outside the norm of x and this is norm x, that is norm x upon norm x is equal to 1. Here 2 times, so it can be removed here. Therefore, this implies that M3 is equal to supremum of norm Ty and y is the element of n. Okay, and norm y is equal to 1. So this expression can be written as this one as per the assumption of y is equal to x upon norm x. What is this? This is the M2. Okay, because here M2, this one with norm x is equal to 1, here vector y, so same expression with vector y here. So M3 is equal to M2. Okay, now if norm x less or equal to 1, x not equal to 0, then we get norm of Tx less or equal to norm Tx upon norm x. It is obvious, because here norm Tx, here also norm Tx. Right side, here multiplication with norm x. Here x not equal to 0, so this is norm x positive. Okay, so norm Tx upon norm x is greater than the norm Tx. Okay, which I am taking supremum of both sides of this inequality. So supremum of norm Tx, norm x less or equal to 1. Okay, here right side supremum norm of Tx upon norm x and x not equal to 0. So with this condition, this is defined norm T, because here we have considered condition A as norm T. Here norm T defined with norm x less or equal to 1. So this is with supremum can be written as norm T, and supremum norm Tx upon norm x by assumption can be written as M3. Okay, equation third. Also by condition D. Condition D, here norm T is equal to infimum K greater than 0, where norm Tx less or equal to K norm x. Okay, and this condition denoted by M4. M4 is equal to infimum K. Okay, so here K, so this can be written as M4. So norm Tx less or equal to M4 norm x. Dividing this by norm x, that is norm Tx upon norm x less or equal to M4. Okay, because here M4 is equal to infimum K and norm Tx less or equal to K norm x, or M4 is equal to infimum K and supremum of norm Tx upon norm x less or equal to K, that is infimum of K. Okay, so supremum of norm Tx upon norm x, this is M3. This implies that M3 less or equal to M4. Also by definition C and D, M4 less or equal to M3. C and D defined here, condition C denoted by M3 and condition D denoted by M4. So by condition C and D, M4 less or equal to M3. From D, norm Tx less or equal to norm Tx less or equal to K norm x for all x belonging to N. That is norm Tx upon norm x less or equal to K. Okay, here norm Tx upon norm x less or equal to K. And from C here defined in statement norm T is equal to supremum of norm Tx. That is, we can write norm T is equal to supremum K. Okay, this M3 equal to supremum of K. Therefore, K less or equal to M3. That is, infimum K less or equal to M3. That is, infimum K is M4 by statement and by our assumption. Okay, that is M4 less or equal to M3. Now from equation 4 and 5, M4 is equal to M3. From 1, 2 and 3, here from 1 norm T greater or equal to M2 and equation to M2 is equal to M3 and M3 greater or equal to T. So from 1 to 3 we can write norm T greater or equal to M2 equal to M3 greater or equal to T. Okay. So here norm T greater or equal to M2 equal to M3 greater or equal to T. So we can write norm T is equal to M2 is equal to M3. Okay. Now from 6 and 7. In 7, norm T is equal to M2 is equal to M3. And in 6, M3 is equal to M4. So, from 6 and 7, norm T is equal to M2 is equal to M3 is equal to M4. Hence, we can say that condition A, B, C and D are equivalent. Next theorem. Let M be a closed subspace of normed linear space N, and let T be the natural mapping, that is homomorphism of N, onto the quotient space N by M defined by Tx is equal to x plus M. Then T is bounded linear transformation with norm T less or equal to 1. Proof. Since M is closed, the quotient space N by M is norm linear space with the norm of the quotient x plus M in N by M given by norm x plus M is equal to infimum of norm x plus small m. Small m is the element of the subspace M. Okay, already we have proved in previous lecture quotient space N by M with this norm as a Banach space. Okay, here defined the mapping T. Here T such that N to N by M. Here mapping defined N to quotient space N by M. Okay, let us prove T is linear. Let x, y belonging to N and AB be scalars. Then we have Tax plus By is equal to Ax plus By plus M as per the statement of the theorem. Okay, here x, then Tx is equal to x plus M. Here Ax plus By as vector, then Tax plus By is equal to Ax plus By plus M. And as per the definition of quotient, we can write Ax plus M plus By plus M. Because we know that x plus y plus m equal to x plus m plus y plus m. Okay, so as per this statement we can write Ax plus By plus m is equal to this one. And again we know that if A is scalar, x plus m is equal to Ax plus m. So this one can be written as Ax plus m and this is By plus m. Again here we apply the statement of theorem Tx defined by x plus m. So we can write x plus m as Tx, that is Atx plus Bty. Therefore, Tax plus By is equal to Atx plus Bty. Therefore, T is linear. Now, prove T is bounded. Consider norm Tx is equal to norm x plus m because Tx is equal to x plus m. Okay, already in statement Tx is equal to x plus m. Taking the norm both side. And again, as per the definition of the quotient space, norm x plus m is equal to infimum x plus small m, where m is the element of m. So we can write this infimum x plus m such that m belonging to m. Okay. This is equal to infimum of k. Hence, norm of Tx less or equal to x plus m. Okay. In particular, m is equal to 0. We have norm Tx less or equal to norm x. Okay. This shows the T is bounded. Norm of Tx less or equal to k norm x. Here k is 1. Okay, that is the condition of bounded linear transformation is satisfied here. Thus, T is bounded. Further, norm T is equal to supremum of norm Tx such that x belonging to n, norm x less or equal to 1, as per the statement of norm T from above theorem. Okay, this one. So this is less or equal to supremum of norm x, because here norm Tx less or equal to norm x. Okay. So this can be written as less or equal to supremum of norm x. And norm x less or equal to 1. So this is less or equal to 1. Thus, norm T less or equal to 1. This completes the proof of theorem. In this lecture, we have discussed norm of bounded linear transformations, bounded or continuous, okay, and some important theorems. These are the references which have been used in this lecture. Function analysis, Dover publication, written by George Beckman and Lawrence Naressi. Introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by V.V. Lemieux. And function analysis, Tata McGraw-Hill, written by Waterwood. Thank you.